So today we are going to finish our discussion of symmetry and parity and show that in fact any symmetric potential v of x, meaning that it is an even function, implies then that the bound state solutions, the bound phi sub n, are all either even or odd functions. And then we're going to go on to prove a series of small but important facts about bound state wave functions in particular. Particularly, we're going to prove that they are real functions. We'll prove their reality, or maybe realness would be a better word, and we'll in particular prove that any bound state phi sub n, even if it might be a complex bound state, right, is actually related to a purely real function, phi sub a of x, and I'll call it that for reasons you'll see later on, by just a physically irrelevant basically normalization constant z. So if you do have some complex solution, it will turn out that all you need to do is to realize that it originates from actually a real solution to the time-independent Schrödinger equation, but it was just multiplied by a normalization constant that happened to be a complex number. We know, though, that those numbers always cancel out and they don't affect any of our probability distributions, so we can just as well seek then real solutions for our bound states. Next, we're going to prove a fact that we'll be using on and off, which is the fact that at least in one dimension, that the bound state solutions are actually non-degenerate, meaning that any two bound states that I have of the same energy En are actually the same state. They might be functions that differ, but if they differ, they only differ up to an irrelevant constant. So I might have two different, what I think are two distinct solutions, but it will turn out that if I do have them, they will actually just be related again by some arbitrary normalization constant. But I do want to stress that that is a fact that occurs in one dimension only. In multiple dimensions, we often have non-degenerate bound states, but frequently we also have degenerate bound states, where for a given En, there are actually a set of physically distinct solutions. Finally, we will go on to prove a very important fact that has very many practical as well as formal uses, something known as the variational principle. And what it states is something that might be somewhat intuitive, but it does bear formal proving, which is namely that for any arbitrary quantum state psi, if I calculate the expectation of the Hamiltonian, the result that I'm going to get will always be at least as much as the ground state energy. And equality here will actually only obtain only if the wave function, this arbitrary wave function that you picked, actually is the ground state wave function. So we will go ahead to prove that. Now, to then go back to our original topic, which is this original topic of symmetry and parity, we had some key results from last time that we will be building upon. First, we had proved that in fact, we defined this parity operation, which corresponds precisely to just changing the direction of your x-axis. So then any function f of x then maps onto, when we look at it with a change in the direction of our axis, it just becomes the function f of minus x. We then associated with this type of an operation of flipping around the direction of your x-axis, we defined a corresponding operator, the parity operator p hat, which then has the definition, as you see here, of just flipping all the values of x. We flip their minus sign. Every time an x appears in my function, I flip its sign. That gives me back the result of the parity operator. And then we proved, in fact, that the square of the parity operator is just the identity. We also proved that, therefore, it is its own inverse, which is an interesting fact. And then finally, we considered what the pure states of this new operator must be. We looked at the pure state equation, and with a little bit of derivation, we were able to prove that the eigenvalues p of the purity operator, the values of the purity, are always either +1 or -1. Those are the only two options for a pure parity state, and the result is that they are then either even or odd functions. So it appears then that what we really want to prove, in order to prove that a symmetric potential v of x leads to bound states being either even or odd, that seems to imply then that if our potential is symmetric, that the eigenstates, that the bound state solutions for symmetric potential must also somehow be pure parity states. And so we will begin now to investigate this issue by considering how it is actually that the Hamiltonian relates to the parity operator.